Any other questions from last week? We talked about the definition of the operating system. Operating systems are not simple, but definition is simple enough. It says that, okay, they are pieces of software, okay, and they are there to help us, okay. They are not application software because they are system software. They are there to operating system routine services. The operating system is there to abstract the computer hardware and the manage the resources. Okay. So they are not word processing programs. They are not compilers. They are not your e-table spreadsheet programs. Okay, they are not applications. They are system programs, and they are there to help you to abstract away the details of the hardware because hardware is complicated. Also, they are there to manage the resources. Manage the resources. What do you mean by that? I mean, using the processor. I mean, dividing the processor time among 50 processes, 100 processes, or the memory, managing the disk and the input-output device is a difficult thing. Okay, good. Let's move on then. We talked about these, and we talked about the kernel mode. And as I said before, this is really important. This one, history of the operating systems. Why? Because we will keep talking about the history of the operating systems because most of the design decisions about operating systems are done in one of these generations. And if we understand why that decision is made, then we understand the operating system. And sometimes, I mean, in today's conditions, sometimes those decisions are not very correct decisions, but well, sometimes you have to leave whatever they have decided in the past, right? So, for example, why we are, do I have my Dawson somewhere? Yeah, well, maybe terminal. Yeah, if I run my terminal, okay, why do I have my prompt like this? C users, T, and etc. Why do I have these kind of, I mean, where does this ls come from? Where does this the directory structure come from, and etc. They are all decided during the early days of computing. For example, the multix is responsible for this kind of decisions most of the time. Okay, it comes from there. I mean, we didn't have to use that kind of syntax notation, etc. But multix made those decisions, and we kept using them because they were good enough. Okay, so let's move on. We talked about, okay, maybe a little recap. Vacuum tubes. In those areas, there were no operating systems because first, they were not invented. Second, people never thought that they would use software to write software. Okay, software is written in machine language using hexadecimal numbers in binary format, and you enter that format. Um, you enter those numbers directly to your computer. That was whole computer. And when later they have invented transistors and computers started getting stronger and stronger. Now they can have very powerful CPUs and lots of memory. In that case, why don't we run more than one program at the same time? Why don't we use software to help us write and run software? Okay, so that's the idea of programming languages and the compilers and the operating system. The operating system is running all the time. It is managing the resources among different programs, which is called multi-programming, right? And then things started getting really small, the personal computers. When the personal computers got smaller, okay, when the computers got smaller, that means what? They are not as strong as the large mainframe computers. So we run into the same problem again of the vacuum tubes. The computer is so weak, so unpowerful that I cannot afford the operating system in the early personal computers. I gave you that Altair example, right? That Altair computer, it was based on 8080 in 1970s. It didn't have an operating system. It was, I mean, you pay $2,000 maybe, but it doesn't have an operating system. So how do you enter your code? You enter code in hexadecimal numbers or in bit by bit, one by one, and that's how you enter your program. Then it's how you run it. Okay, so that it means what? Whatever they were having as problems in 1940s, 50s, we were having the same problem in 1970s with the PCs. Okay. And the same thing happened with the mobile computers or the embedded computers in 1990s, 2000s, because very small computers, they don't have enough power to they don't have enough power to run the operating system or complicated operating system. Okay. So and then okay, when okay, for computers, and when the time comes to fourth generation computers and the operating systems, we are not optimizing the efficiency of the computer anymore. Now we are optimizing the interactivity, responsiveness. My computer has to be responsive. Whenever I click a button, it should give me the result immediately back. Okay, so I am not trying to utilize the CPU 100% of the time because CPU is cheap. It is $1,000 now. My time is more, as a user, my time is not more important. Okay. Fifth generation again, interactivity with the mobile computers, cell phones, smartphones, tablets. Again, interactivity is important, but security and battery management is important too. So I am trying to optimize something else. So if you are designing a mobile computer operating system, you have to keep in mind that it should be interactive. Okay, it should be responsive. Also, it should be very secure in terms of keeping your data, and it should not run your CPU 100% of the time. That's exactly the opposite of what you do in 1960s, right? In 1960s, you don't care about your power. You care about your time. In 1990s, I care about my power. I cannot use my CPU 100% of the time because my battery would not last more than half an hour, right? In that case. So always try to keep the battery usage in mind. And then we came to computer hardware. I mean, as I said last time, we are not trying to teach you computer hardware in this course. That's what you did already in your computer architecture course, right? I'm just trying to make a review and trying to introduce some of the hardware concepts, and this is our main system architecture. Simplified, conceptualized system architecture. We said that we have our CPU, we have our memory, okay, and they communicate over a bus. Usually this bus is 16-bit or 32-bit or 64-bit wide. So whenever the CPU talks to the memory, okay, it can get 64-bit at a time in nowadays CPUs, popular CPUs, okay? And this memory management unit is within the CPU. It is responsible for, remember, making this virtualization of the memory, virtualizing the memory so that each program would think that they have their own memory, starting from address number 0 to some large number. Okay. These video controllers are hardware components. Okay, they are hardware components. They are connected to the CPU. They are connected to the system bus, and they communicate with the CPU using the system bus. These are the video controllers. Okay, and again, the CPU can modify, can communicate with these controllers in kernel mode only. Okay, in kernel mode only. The CPU has sometimes special instructions. For example, let's say this one. Keyboard controller has special location in it. It has special location in it. Another special location. These are memory locations. Let's say this memory location will give you the key pressed by the user on this keyboard. Okay, let's say there is a number 27. Let's say 27 corresponds to one of the keys here. Let's say this one is for the caps lock. And let's say this one is for the scroll lock. Okay. So communicating with the keyboard is not a very difficult thing actually. All you do is, if there is a number here, 27, that means that somebody pressed the key number 27, whatever it is. If this register is 1, that means that the caps lock is on. So there are, for some CPUs, there are special instructions, I/O instructions, okay, that can read these special locations. And this is how you communicate with the keyboard controller from the CPU. Okay, the same thing with the monitor. Okay, to put a number, let's say these are the old days. I have 80 columns. Okay, 80 columns and 40 lines. Okay, and I like to put a letter A at this location in my terminal. Okay, in this case, the terminal is like this. Okay, let's say this is 80 by 40, and I am trying to put a letter A at that one. So in this case, in my video controller, I have exactly the same memory arrangement, 80 bytes by 40 bytes. And if I put number 65, can I make it even? Yeah, if I make this number 65 in here, or 6, it will print, it will put the letter A in that location. That's the job of the video controller. Maybe this communication between the controller and the monitor is difficult, complicated electronically. I don't care. All I do is I modify this memory inside my video controller, and the desired screen will be produced by the monitor plus the video controller. Okay, so for all the I/O devices, this is what I do. This is, let me try to, okay, this one and this one. I don't have anything open. Yeah, good. Okay. All I do is communicate with the controllers, and rest of them will be handled. This controller is simple. This is more complicated. This is very complicated because USB controller has to communicate with many different types of USB devices, right? And the hard disk controllers are difficult too. I mean, they are complicated. Remember, only for the SATA, 400 pages of specification only. So this hard disk controller is something complicated. Sometimes hard disk controllers are multi-CPU computers. Sometimes they have to use computers as the controllers, right? Because because it's complicated. Okay, good. So let's move on. Are there any questions
Sir,
about
may
the
I ask
array
something?
structure? Sure. Just a minute. Let me see your name. Okay,
Asma
okay.
Afare. Can operating system use the hardware interchangeably? What I mean is that in FPGA, hardware can be programmed differently according to our coding. Can our computers do this via operating system?
I am not sure what you have asked, but I mean, during the runtime, operating system doesn't like much. If it's a very specialized system, and if the operating system is written that way, yes, you can. But in general purpose computers, you don't expect that kind of hardware changes during the runtime. If you are talking about FPGAs, I am not sure if everybody knows about the FPGAs. FPGAs are specialized computers, let's say, or the electronic circuits or the electronic devices that can be programmed in a way that you change your hardware configuration. Okay, so those are very, very specialized. And if the operating system written that way, yes, yes, you can. But our regular operating systems of Windows and Unix and OS 10, we don't go that kind of details actually.
Because when we use the virtual machine, some drivers cannot exist. For example, the microphone can't open, and when we install some drivers, it can be used via that driver.
Yeah.
This is about the operating system or another thing.
No, no, no. For the virtualization, let me go to that slide again. Remember that I showed you. For some reason, I am getting this. Okay. Okay. This is what happens with the virtual. At the bottom, I have the real hardware. On top of it, there is this virtualization layer software. Okay. This software acts like a very primitive operating system. All it does is translate the real operating systems. Okay, these are three of the same operating system running on top of this, translation abstraction layer. Okay, whatever I get, I translate it to the hardware. So when you install a new mouse driver to your virtualized machine, you are adding more capabilities to this translation layer or the virtualization layer. Okay, you are not changing your hardware. Let me in fact do this. Okay, usually we use this kind of virtualization. I have my hardware at the bottom. Okay, I have a mouse, I have my network driver, video controller, etc. On top of it, let's say I am running Windows. On top of it, I am running Type 2 hypervisor, or VMbox, and etc. On top of it, I am running Linux, right? Let's say on Linux, I am trying to access the mouse. Okay. When I need the mouse, this guest operating system, it says that read the mouse register for me. Okay. That's the guest operating system. It thinks that it is accessing the controller of the mouse device, but in fact, it is saying something to this type 2 hypervisor. If the type 2 hypervisor is not capable of translating that request to the host operating system, then this guest operating system cannot use the mouse. So this type 2 hypervisor should be able to translate that request, read that byte from the mouse controller's register, then things are bad. But if I appropriate mouse into this type 2 hypervisor, okay, then I'm going to be fine. So what you are asking is, you're not changing the actual hardware, okay? You are adding more software so that your type 2 hypervisor can handle that kind of hardware request translation.
Okay, thank
This
you.
This virtualization thing is very interesting, and it might seem a little bit weird and a little bit impossible. How could that happen? But understanding the virtual operating systems or virtualization, containerization is something key to understanding how an operating system works actually. For example, let's look at this one. This is interesting, really. This is an application program. This is an application program. This host operating system don't know that these two are application programs, and this is another type of operating system. No, it thinks that this is another application program. Okay, that's what the host operating system thinks. So in this case, in this picture, only this host operating system runs in kernel mode. This one doesn't run in kernel mode. This guest operating system doesn't run in kernel mode, but if it doesn't run in kernel mode, how could it modify the memory management unit register, right? Because this one has to modify the memory management unit so that these applications can run like they think that their memory is reserved, right? So it's kind of weird. How could this happen? We are going to see this, but when this operating system tries to access the memory management unit, it will cause an interrupt, right? Because a regular program tries to access the memory management unit. Who's going to handle that interrupt? Host operating system. Now, I asked the host operating system, if you get such a request from this guest operating system, then let it go through, okay? Then this operating system will behave specially when the requests come from this guest operating system or type 2 hypervisor. Okay, that's why it is a little bit different to install your virtual machine on your operating system than installing a regular program. Okay, so we'll talk about them when the time comes, hopefully at the end of the semester.
Can I ask a
Good,
question?
and sure, yeah, these are all good questions, yes.
Why hard drive doesn't connect to the CPU like main memory?
Say that again, I did not understand exactly understand your question.
Why hard drive does not connect to the CPU like main memory?
Well, it is like that. What do you mean? I mean, CPU and memory are connected over the system bus. Controller and the CPU is connected over the system bus. They are connected exactly the same way.
But hard drive is slower. Doesn't the reason is
Well, I
the
mean, maybe. Well, this is a very simple architecture diagram to answer your question. Maybe I should skip a little bit. Can I find? Yeah, this is a more realistic system diagram. Okay, hardware system diagram. This is our CPU side. Okay, they have more than one CPUs, two cores. Okay, they have their own caches, and there's a shared cache. Then I have my GPU cores, graphics processing units, our monitor, etc. And this memory is connected directly to this module. Then I have this platform controller hub connected with a special bus. Then rest of the hardware is connected to this one. I think your question relates to this one. Memory and the graphics are connected more directly, okay, in a more efficient and faster way to the CPU because we communicate with the memory in a more frequent way, and we could have to communicate with the memory in a faster way. It has to be very, very fast. Okay. The same thing with the graphics. Nowadays, I need to send Okay, I need to send a gigabytes of data per second to the graphics card so that I have nice animations when I play the games. So that communication has to be very, very fast and efficient. Okay, but the same thing doesn't have to happen with my USB 2.0 devices, such as my mouse or that kind of stuff, right? So I don't have to make all of these as fast as the graphics card or the memory. They can stay slow, okay? I can make them fast, but that would increase the cost of the computer hardware. I don't want to do that. Did I answer your question?
Yes.
Well, basically what you ask is the operating system question. It's a computer hardware question, but as I said before, without understanding computer hardware, it is very difficult to understand why operating system is doing something. Okay, good. Let me go back. Hardware, let's talk about the processor now, which is the most important hardware of all, okay? So the hardware processor is the brain of the computer. Why do we say that? Because it executes the instructions, right? It does whatever needs to be done. It controls everything, right? So it's the brain of the computer. So regular fetch, decode, execute cycle is valid, right? It fetches the instructions from the memory. It understands what those instructions are, and it executes them and repeat the same process. I mean, this was decided, okay? This was decided in 1940s, 50s like that, and we still keep using the same CPU design, okay? And inside the CPUs, I have registers, many registers, okay? What is a register? Register is, of course, a special. How do I erase this? Do I erase this like that? Cannot do this. Okay. It looks like, okay. Let's say this is my CPU. Something is holding my CPU. It is 14%. No. What is holding my CPU? Edge is, wow, see? My memory is filled up, right? Is that correct? Where is my memory? Yeah, it is here. It is all it is all filled up. It is, I don't know why it is happening. And who is using my memory? My tasks. Let me do this. Not much. These are all stuff. Let me terminate this thing and start it again. Teams is using lots of it. Maybe during the break I should reboot my computer, but I don't understand why. See this? Each of them is a separate process. Many of them are not doing anything. Okay, they are not using any CPU. They are waiting there. They are all demons. Okay, like the spooler. They are waiting for something to happen. They are operating system processes most of the time. They wait until operating system asks them to do something, but they have to wait in the memory. But sometimes operating system says that this guy is at the memory and it is keeping up memory. Why don't I keep this on my desk? Whenever needed, I can load it from the desk. Okay, that's going to be slow, but this process doesn't run very frequently anyways. So I can keep them on my desk. Still, I am not. This Teams thing is very Why do I have so many Teams processes? I don't know. I can try killing some of them later, not now. Okay. So let me close this thing and open it again. No, don't do that. Okay. Much more responsive, I guess. Okay, erase this part.
Professor, can I ask a question?
Sure, yeah.
The daemons are does daemons are belong to OS? I mean,
Yeah, all the daemons are operating systems processes. If you
okay.
call it a daemon, yeah, it's an operating system process, but you might say that anything that sleeps is an operating system process. Of course not, no.
Mhm.
Because I mean, if I have 10 processes running, one of them runs, the others sleep, right?
Are they used for handling system calls? For that reason, maybe I think that for that reason they are waiting.
Yeah, most of the time, yes. Most of the time, if you have something sleeping by the operating system, it is task is, let's say, to get some data from the disk, okay, to present it in a known format. Yeah, they sleep, and whenever there is a job, operating system wakes that process up. Okay, it handles it, it makes the data ready, and it has operating system's data is ready. An operating system knows which process asks for that data, and operating system wakes up that process. Okay.
Okay.
So inside my CPU, okay, there are registers. Okay, what's a register? Register is like special memory location. Okay, register number 1, register 1, register 2, register 3, register 4, and this is inside my CPU. And registers are very fast, very fast to uh, access, to modify. Okay, and they are not part of the memory; they are part of the CPU. So it takes only a single clock cycle to access them. That's why we like them a lot. So that means what? That means whenever the number of registers and the capacity of register is good enough, write your programs in a way that they use only the registers, okay? Well, I mean, in C or C++, we don't talk about registers, but in assembly, you talk about registers, right? When you write assembly programs, okay, try to write programs that doesn't refer to the memory at all, that uses the registers all the time. Okay, so I have registers and I have special registers such as the program counter, right? The program counter, which is called sometimes PC, program counter. It program counter is like a pointer, Let's say this is my memory. This pointer points to some location in my memory, and it tells that I am executing this position. So this is how the CPU knows where it is executing. Okay, when I execute this line, something happened with my now pen. When I execute this line, that address, I increment my program counter by 1, and CPU say that I am going to increment this new program counter position now. That's called That's called a program counter. And I have the stack pointer. You know what stack is. Stack is there to keep our data about local variables, the function return position, and etc. That's important too. So there is a stack pointer like the program counter. And the program status word, PSW, it keeps, the most important thing maybe that it keeps is the kernel mode. Okay, here is the kernel mode. Okay, the kernel mode tells the CPU that if it is running in the kernel mode or not. If it is running in kernel mode, then it is allowed to do anything it wants. It can access any memory location, or it can program the I/O registers. It can program the interrupt controller. It can program the memory management unit, etc. Right? That's the kernel mode. During the program run, if I have an application program, a regular program, a user program, when I am executing my program on CPU, I am not in kernel mode. Okay, I am not in kernel mode. I am in user mode. If I am in user mode, then you know my limits, right? If I am in kernel mode, though, I can do whatever you want. If the CPU executes an instruction in the user mode that tries to access the memory management unit registers, then the CPU is going to create an interrupt. Interrupt means that stop whatever doing, okay, stop whatever you are doing, and immediately go to the interrupt handling unit function. And interrupt handling function is, of course, belongs to the operating system. Now I am in the kernel mode and I'm handling the interrupt. Okay. And most of the CPUs, they have this special instruction called system call. Okay. Our regular programs, they say that, okay, I need the help from operating system. I am making a system call. Please get me a character from the keyboard. Okay. So I make a system call. As soon as I make a system call, I am in the kernel mode and operating system is executed now. Operating system takes control of the CPU. It is in the kernel mode and it knows what is asked. If it is something it can do, then it will do it. Otherwise, it's going to say, no, you don't have any permission to ask for this kind of a system call. I will terminate you, or I will let you know that I am not doing anything. Okay. Any questions? Okay, it looks like I think I will take some break, but okay, let's take some break until 9:35. Make this a little bit bigger. Okay, let's be here around 9:35, and I will handle whatever is happening with my operating system. Okay, 10 minutes or whatever, 50 minutes, 30 minutes.